Sorry about that, the connection got interrupted. So let us continue. And we were just discussing about this okay, so we can just equate them and rearrange. So we get this as our a of n plus 1 plus r and alpha n plus 1 will be equal to over a of n of n minus r alpha. Okay, one second. This is our minus and this is plus. And we are having two linear relationship between the successive levels. So we can just replicate them and we can say that we are having two linear relation between successive levels. And therefore we can write that a n plus 1, and we are having this as our from equation number 3 we can write a n plus 1 beta r alpha n plus 1 is equal to minus a of n plus beta r alpha of n, and we can write it as a n plus 1 plus r alpha n plus 1 is equal to a of n minus r alpha of n. Okay, so these are the two equations of our successive levels, and we can just solve them. And okay, and in this case we have to remember that we are dealing with this infinite stack of our cylinders. Okay, so we are going to find out the geometric ratio that is going to help us to find out the solution. Okay. And for that we are given that we have an infinite tower and this infinite tower, let us consider that we are having a constant scalar that is our r, which we have treated as a common ratio. So we have a constant scalar and that scalar is suppose given as our r. Therefore we can write that our a n plus 1 is equal to r a of n, and our r times alpha n plus 1 is equal to small r capital R a of n. Okay, and this is true for all values of n from our lowermost up till infinity. And therefore we can write the equations. So we can say that our r a of n plus beta small r capital R alpha of n will be equal to minus a of n plus, and this is our beta r alpha of n. and we can just combine the like terms. So we get this as our r plus 1 a of n is equal to beta 1 minus r alpha of n. And from our second equation, and this equation is going to give us r a of n plus r alpha of n is equal to a of n minus r alpha of n. Therefore, we can write that our r minus 1 times a of n is equal to minus r plus n r alpha of n. And let us call this equation number 1 and this as equation number 2. So these are the two algebraic equations, and from here we can just solve them, and we are going to eliminate our this r alpha of n and r alpha of n. Therefore, we can say from equation 1 and 2, from equation 1 and 2, we get this as r alpha of n is equal to our, this is minus, and we have this as r minus 1 divided by r plus 1 times a of n. And this gives us that r plus 1 a of n is equal to our beta, and this is 1 minus r, and this is minus r minus 1 r plus 1 and times a of n. And we can just solve this, and it will be giving us that we multiply both sides by r plus 1, and first of all let us cancel out this a plus n, and we get this our r plus 1 will be equal to, this is beta 1 minus r and minus r minus 1 r plus 1. Okay. And we multiply both sides by r plus 1, so we get this as our, okay, so we get this as r plus 1 whole square is equal to beta, and from here we take as minus common, so this will be minus minus plus 1 minus r whole square, r minus 1 whole square, r minus 1 whole square. Therefore, we get that our r plus 1 divided by r minus 1 will be equal to plus minus square root of beta. And we can further solve it, and we can also find out our r. So this r will be coming as our 1 minus square root of beta and divided by 1 plus square root of beta. And if we want to solve it further, we can say that there is no need to solve it further. Okay, so this is our the relationship of our radius, and we can use the first relationship which we are given to us, that is our r alpha of n is equal to, this will be coming as r minus 1 r plus 1 times a of n, and this will be coming as our r alpha of n is equal to square root of beta A of n. So this is the relationship between their angular acceleration as well as the linear acceleration. And we can now relate with the bottommost, which is our Planck's acceleration. Therefore, we can say that bottom Planck acceleration, which is our A, and for our first cylinder acceleration that we have considered nth, and for that let us put that n is equal to 1. Therefore, we get that our A will be equal to A of 1 plus r times alpha of 1. And therefore, we can also write it in terms of a beta. We get this as A is equal to A of 1 plus beta times A of 1. Therefore, the bottommost acceleration, that is our A of 1, will be equal to square root of beta and 1 plus square root of beta times A. So this is the acceleration, or we can say the linear acceleration about the bottommost Planck cylinder. And the next question, so this is the third question which we are going to solve today, and it states that a small solid ball of mass m and moment of inertia beta mr square rests on the top of a smooth fixed sphere of radius r. There is sufficient friction between the two surfaces to ensure pure rolling as the ball begins to move. The ball is given an infinitesimal disturbance and rolls down the sphere without slipping. And assuming that r is very much smaller than capital R, determine the angle measured from the top at which the ball loses the contact with the fixed sphere. And second, discuss quantitatively how the result would change if the ball's radius is comparable to or larger than the radius of r of a fixed sphere. So in this case, we are supposed to find out the angle of loss of contact, and that we can know that if we put normal is equal to 0, and that solve our purpose. So first is our angle of loss of contact. Angle of loss of contact, and this is under the condition that our small r is very much less than our capital R. And we are given that we have a bigger ball whose radius is given as small r, and above that we have a small ball and its radius is given as small r. So therefore, the total height from the center will be equal to our r plus capital R. And if we rotate it by angle of theta, therefore we can say that the velocity v will be equal to r plus small r and theta first derivative. Okay, and we can easily calculate their you can say the energy conservation we can apply, and for that we can just suppose this is our center of the small one and this is center of a bigger one, and this total height is our r plus capital R, and the center is going to rotate, and let us suppose at this particular point the angle is given as theta, and here the velocity is our v, which we have just written here. And therefore we can say that our this total distance is our r plus capital R, and this is a radius r, so this will be our r cos of theta. Therefore we can write that our conservation of energy and this conservation of energy will be because the sphere is rolling is going to have two types of motion. One will be its linear translational, and other one will be rotational. And therefore we can say the conservation of energy, we can write this will be equal to our the decrease in the potential energy, that is our mg, and we have this as our r plus capital R, and 1 minus cos of theta will be equal to the translational plus rotational. And there is no slipping, therefore we can write that for our pure rolling, or our no slipping, at the contact, and let us assume that the ball's rotation is through angle of phi. Okay. So we have pure rolling, no slipping, and we can say that our ball's rotation is through angle of phi. Okay. Therefore we can write that our r of phi will be equal to r plus small r times theta, and from here we can write the angular, that's omega, will be equal to first derivative of our phi, and that will be equal to our r plus small r divided by small r and theta first derivative. And therefore if we substitute the values, we can write this will be equal to over half m v square plus half I omega square, and we get this is half m v square is our, rather v is our r plus r theta first derivative, so we get this as r plus capital R whole square theta first derivative, and our plus 1 by 2, and the moment of inertia I is given to us as our beta mr square. So this comes as our beta mr square, and omega square will be equal to our r plus small r divided by small r whole square and theta first derivative square. And from here we can just take the common, and we get this as 1 by 2, and we have this as our m r plus capital R whole square, and we can take theta first derivative also common, and this will be coming as 1 plus beta. Okay. And this will be equal to our the conservation of energy, that is our left hand side. Okay. So you can say that this will be equal to our mg r plus small r and 1 minus cos of theta, and here our m and square and this cancels out, therefore we can say that our it gives us half r plus capital R theta first derivative 1 plus beta is equal to g1 minus cos of theta. And from here we can use the velocity equation and find out our velocity. Okay. Therefore, we can say that our velocity square is equal to r plus whole square theta first derivative, and this will be equal to g r plus r and 1 minus cos of theta divided by, and this comes as 2 and this comes as 1 plus beta. Okay, so this is our velocity, and we can find out the radial acceleration also, or we can say radial equilibrium, and that will be because of our centripetal force. So we can say we are having a radial equilibrium, and under radial equilibrium we can write that our m v square r plus r will be equal to mg cos of theta minus n. N is our normal. We can just draw an approximate figure for that, and it is suppose somewhere here, and there will be normal, and we are having our mg, and the angle it moved is our theta. So we can divide mg into two components, our mg sine of theta and other one will be mg cos of theta. So this is going to give us the centripetal. Okay, and for lift off, obviously value of n will be equal to 0. So we can say that for ball loses contact, which means value of n is equal to 0. Therefore, we can write that our m v square r plus small r is equal to mg cos of theta, and we can solve it for cos of theta because we already know our v square, and v square is our 2g r plus r. Okay, so let me substitute it. So we get this as m upon r plus small r, and this comes as 2g r plus small r 1 minus cos of theta and divided by 1 plus beta, and this will be equal to mg cos of theta. And here this r plus r and m, g and g cancels out. Therefore, we get this will be equal to our 2 1 minus cos of theta is equal to 1 plus beta cos of theta, and which can be further written as this will be coming as our 2 is equal to 3 plus beta cos of theta. Therefore, we can say that our cos of theta is equal to 2 upon 3 plus beta. So this is our angle of where the ball is supposed to lose its contact. Okay. And in this case, we can clearly see that our theta is only dependent upon our beta. Okay, so there is no factor that is our r plus r. Okay, so it means this kinematic relation is going to hold for each and every relationship unless and until there is considerably change in our radius. Okay. Because in the part B, its state is that result will change if the radius r becomes comparable or larger than the radius of our small r, and in beta is only dependent upon our small r. Okay. So in this particular equation, which we calculated as value of theta, so our beta is only dependent upon our small r. It is independent of our capital R. Okay. Unless until this r becomes very close to this capital R, there is not much of effect on our this value of our theta. So the kinetic equations are going to hold. Okay. So this completes all the 3 questions for today. Thank you.